Earlier in the course, we went through the intuition behind the modern portfolio theory that was developed by Markowitz. In this video, we're going to work through the details of how you find the optimal portfolio. Hopefully you have a vague recollection of the optimal portfolio, but if not, we're going to review it now anyway. In this diagram, we have on the horizontal axis risk as measured by standard deviation, and on the vertical axis we have returns. And recall, we can plot all combinations of stocks on this diagram, and that's what we see represented by the X's. And we learnt that all risk-averse investors will want to invest in what we call efficient portfolios. What is an efficient portfolio? An efficient portfolio is one that, for a given level of risk, maximizes expected returns. Remember, as a risk-averse investor, we like expected returns and we dislike risk. So we're going to like portfolios that maximize expected returns for a given level of risk. And we can show on here the combination of all efficient portfolios. And it's called the efficient frontier. And it starts from the minimum variance portfolio and moves upwards along the edge of the feasible set. The line in red is the efficient frontier. We then introduced a risk-free asset into this problem, and we said, what would investors do now? It turned out that all investors wanted to invest in some combination of the risk-free rate and the optimal portfolio. The optimal portfolio is indicated on this graph. Why did all investors want to invest in some combination of T-bills and the optimal portfolio? The answer is that it maximized their expected utility. Alternatively, we can think about the trade-off between risk and return. Investing in a combination of the optimal portfolio and T-bills meant that investors would maximize the returns for each unit of risk that they took on. In other words, we maximized the slope of this line. The steeper the slope, the more return we get for each unit of risk. That's what risk-averse investors want. In equilibrium, we saw that all investors will hold a combination of T-bills and the optimal portfolio. And we called this line that connects the T-bill rate to the optimal portfolio, we called it the capital market line. What we're going to do today is work through how you actually calculate the optimal portfolio. Recall, it was going to be of great use to investment managers, because rather than having to find out all the details about individual investors and their preferences, all the investment manager has to do now is find out the investor's level of risk aversion, and then they can decide how much to invest in T-bills and how much to invest in the optimal portfolio. So it really simplified things for investment managers. Let's set about finding the optimal portfolio. Modern portfolio theory was built out of expected utility. Here's the utility function we've been working with throughout the semester. The expected utility is equal to the expected returns on the project minus lambda times by the risk of the project, and the risk here is measured by the variance. Markowitz assumes that all people are risk averse. In other words, lambda is greater than 0. If an investor wants to find the optimal portfolio, what they're going to do is maximize their expected utility. So investors want to solve the following problem. they have to maximize the expected excess returns on a portfolio minus lambda times by the risk of that portfolio. This is the function that investors will be maximizing. Notice that we're looking at excess returns. We're looking at returns over and above the risk-free rate. We are assuming that there is a riskless asset in this economy and that we can invest in it. What do investors choose though when they want to maximize their expected utility? What is it that they choose? Well, the investor is trying to work out how much to invest in each stock. That means the investor is trying to choose the weights to invest in each stock. So we're going to be maximizing with respect to the weights. But where do weights feature in our formula here? We have expected excess returns on a portfolio, and we have the risk of the portfolio. We can rewrite this in terms of the weights. This is where our matrix algebra comes in. The expected excess returns on the portfolio can be written as W transpose all multiplied by mu minus RF, where mu is the set of expected returns for all assets and RF is the risk-free rate. Then we're going to subtract off lambda times by the portfolio variance. And we've seen that portfolio variance can be written as W transpose times by S times by W, where S is the variance covariance matrix. Now you can see what we're trying to maximize. We're going to choose our weights and maximize expected utility by changing the weights that we invest in each stock. There is one constraint on this problem. The weights, remember, must add up to 1. But there's a trick to get around this constraint, so we're going to ignore it for the time being. We'll briefly review the notation, although I think you probably are used to it now. Mu represents the expected returns. It's a column vector, and there are m risky assets. S is the m by m variance covariance matrix. W represents a column vector of weights, and we know that the weights must add up to 1. And finally, we know that the expected returns and variance on a portfolio are given by W transpose times by mu, that's the expected returns, and the variance is given by W transpose times by S, the variance covariance matrix, times by W. To work on the intuition, let's think about the two-asset case. We want to maximize utility. How do we do that? We do that by changing the values that we invest in each asset. In the two-asset case, we've got the amount we invest in W1. In the two-asset case, we've got the amount we invest in asset 1 and the amount we invest in asset 2. In the two-asset case, we have the percentage we invest in asset 1 and the percentage we invest in asset 2. We can actually draw this on a diagram because in the two-asset case, the percentage we invest in asset 2 has to be equal to 1 minus the percent we invest in asset 1. Suppose we start by holding virtually none of asset 1. As we increase the amount we hold in asset 1, we see that expected utility starts to increase. We keep investing then because we want to maximize our expected utility, so we keep investing more into asset 1. And we're seeing still expected utility is increasing. So we keep investing an even higher percentage into asset 1. And at some point we find that expected utility has reached a maximum. We can't increase expected utility any further. We then add a bit more of asset 1 to our portfolio, so we increase the percentage still further, and we see expected utility starts to fall. What would you do if you were the investor? Well, you'd go back to the optimum, where you maximized expected utility. The interesting thing is, the point at which expected utility is maximized is the point at which the gradient of the slope is equal to 0. This is the key insight. And that's what you're going to have to remember when we go forwards to solve for the optimal portfolio. Expected utility is maximized at the point at which the gradient of the slope is 0. That's what you're seeing on this graph. In the 2-asset case, it's pretty easy to calculate the percentage allocated to each asset, either in Excel or even by hand. And we can draw a diagram, just as the one you see here. Just like the one you see here. In reality, we've got thousands of assets, so the problem's a bit more involved. The question is, how do we solve the problem when it's more complicated? We're going to have to think about optimization and differentiation. How do we calculate the slope of a line? The slope of a line is calculated as the change in y divided by the corresponding change in x. We've seen this in high school. We've also seen how you can calculate the slope of a curve using differentiation. And the basic rule of differentiation is that if y equals x to the power n, then dy divided by dx is equal to n times by x to the power n minus 1. This is the slope of the line. With differentiation, we can calculate the slope of any curve or function using this formula. How does this work when we consider the optimal portfolio? We want to maximize expected utility by changing the amount we invest in each asset. What we know is that the investor's expected utility will be maximized when the gradient of the slope on the utility function is equal to 0. We're going to use differentiation then to calculate the gradient of the slope, and we know that utility is maximized when the slope is equal to 0. So let's work through this problem. We want to maximize, with respect to the weights, we want to maximize the expected excess returns on our portfolio minus lambda times by the risk of our portfolio. This is the function we're maximizing, which we can rewrite using our matrix notation. So we have W transpose times by mu minus RF minus lambda times by W transpose S times by W. We know that if we have a function y which equals x to the power n, then dy by dx is equal to nx to the power n minus 1. We're not dealing with standard algebra though now, we're dealing with matrix algebra. W is a matrix. Fortunately, differentiation rules also apply to matrices. The difference is that we don't see W squared. What we see is W transpose W. This is the equivalent, using numbers, to W squared. That's the only thing you have to remember. I do not want you to go away and think about learning all the rules of matrix differentiation. The intuition is very similar. Let's differentiate our expected utility with respect to W. What do we get? The expected utility by dW is going to be equal to, consider the first expression. We've got W transpose times by mu minus RF. Let's use the formula here to work out what we do. We have W, effectively it's to the power of 1. That means when we differentiate it will be 1 times W to the power 0, which is equal to 1. What we will be left with is mu minus RF. Now let's consider the second part. We've got W transpose times by S times by W, and we know that W transpose W is approximately equal to W squared if we're thinking about differentiation. What happens? We get minus 2 times by lambda times by S times by W. We've now differentiated expected utility with respect to the portfolio weights. To solve the investor's problem, we know that expected utility is maximized when the gradient of the slope is equal to 0. This is the gradient, and we maximize expected utility if the gradient equals 0. So let's just set the gradient to be equal to 0. We're going to get mu minus RF minus 2 lambda SW equals 0, which leads to mu minus RF is equal to 2 lambda SW. We want W on its own. How do we get rid of S? S is the variance-covariance matrix. This is where we have to think back to our matrix algebra rules. Suppose we pre-multiply both sides by S inverse. What's going to happen? Let's work it through. We're going to get S inverse times by mu minus RF, and that's going to be equal to 2 times by lambda times by S inverse times by S times by W. What do we know though? We know that S inverse times by S is equal to the identity matrix. So we get 2 lambda I times by W. What do we know about I times by W, where I is the identity matrix? We know that I times by W is equal to W. This is like 1 times by W. So we get 2 lambda W. We can rewrite this as Z equals S inverse times by mu minus RF, and Z is equal to 2 lambda times by W. We've now solved for Z, and Z is equal to 2 lambda W, but we want W. Well, here's the trick, because we said earlier that the weights must add up to 1. What we do to find W for an individual stock, so WI is going to be equal to ZI. ZI is one component of the matrix Z, divided by the sum of all the Z's from J equals 1 to M. we can rewrite that. That's going to be equal to 2 times by lambda times by Wi. That's the weight on the individual stock. All divided by the summation from j equals 1 to m for 2 lambda Wj. We can simplify this formula now. We get 2 lambda Wi all divided by 2 times by lambda times by the summation from j equals 1 to m Wj. We can take the 2 lambda outside the summation because it's not linked to j. It's not stock specific. It's common to all stocks. And now look what happens. We have 2 lambda at the top, which cancels with 2 lambda at the bottom. We're left with Wi divided by the sum from j equals 1 to m Wj. What do we know about the sum of Wj? We know that all the weights must add up to 1. So we get Wi divided by 1, which gives us Wi. That's how we calculate the weights for the optimal portfolio. This is the problem investors solve, and this is the solution. We've found the optimal portfolio. We could also find the efficient frontier. To find the efficient frontier, or indeed more generally, any portfolio that is on the envelope of the feasible set, we can use a very similar approach. All we have to do is replace the value of the risk-free rate with different alternative values that we'll call C in the maximization problem. Then you resolve the maximization problem with this different value of the risk-free rate. The efficient frontier will consist of all the points on the envelope above the minimum variance portfolio. And we can see that on a diagram. This is the problem we've just solved. We had RF, and we calculated the weights for our optimal portfolio here. And to calculate the efficient frontier, we're just going to change the value of the risk-free rate. Maybe we start here. And we recalculate our optimal portfolio, gives us a point here. And we can do the same for lots of different values of the risk-free rate. And when we plot all the solutions, we can trace out the efficient frontier and the envelope of the feasible set of portfolios. And that's how you calculate the envelope of the feasible set of portfolios. Reminder, the envelope is here. That's all I want to cover in this video. We've now seen how to calculate the optimal portfolio, and in the next class we're going to do this in Excel. See you in class.